Hello, in the lesson of today, we are going to continue talking about the Bessel functions, and we are going to show some expressions that we have been using in recent lessons where we were talking about the Fourier Bessel series, right? But we were using a famous differential recurrence relation that we haven't shown. So the purpose of today is to show that relation that we have been using. Okay? Just a first recall that the Bessel function states that x squared y double prime plus xy prime plus x squared minus nu squared y is equal to 0. Okay, and well, we are not going to show what is the solution for this equation, right? I'm just going to tell you that, as you should know, the solution of this is the Bessel functions of order nu, right? And that function stays for a j sub nu of x is equal to the sum from n equals 0 up to infinity of minus 1 to the n divided by n factorial gamma of 1 plus nu plus n, and then this multiplies x divided by 2 raised to the 2n plus nu. And you should remember that the gamma function is defined as gamma of a number z equals to the integral from 0 to infinity of t to the z minus 1 e to the minus t dt, right? This is just to define the gamma function that is here at the denominator. Okay, so these are the Bessel functions of order nu that are the solutions of the Bessel equation that is over here. Perfect. So we are going to make use of these Bessel functions to show the recurrence relation that is the purpose of this lesson. Okay, so we are going to start by taking the derivative with respect to x of this Bessel function, right? So we are going to get j sub nu prime of x. This is going to be the sum from n equals 0 to infinity of minus 1 to the n divided by n factorial gamma of 1 plus nu plus n. And then here we are going to take the derivative of this, right? Because here is the dependence on x. So we will get 2n plus nu, then x divided by 2, 2n plus nu minus 1. And then due to the chain rule, we need to multiply by 1/2. Okay, so here it is easy to see that we can see this element as x divided by 2, 2m plus nu times 2 divided by x, right? Just due to this minus 1 that we have at the exponent. And then we can cancel these 2 with these 2 that we have here, and we are just left with an x dividing, right? That we are going to take out of all the sum. So this is going to give us that j sub nu prime of x is equal to 1 divided by x, the sum from n equals 0 to infinity of minus 1 to the n, 2n plus nu divided by n factorial gamma of 1 plus nu plus n, and then this multiplies, right? X divided by 2 raised to the 2n plus nu. Okay, and we are going to take this x that is here to the other side of the equation to multiply this j sub nu prime of x. Okay, perfect. So with this expression that we have here, we are going to split this sum into two pieces, right? One for this 2n and the other one for this nu, right? So we are going to get that x, j sub nu prime of x, is equal to the sum from n equals 0 to infinity of minus 1 to the n, 2n, divided by n factorial gamma of 1 plus nu plus n. That multiplies x divided by 2 to the 2n plus nu, and then plus, and we are going to take out the nu out of the sum, so it will be nu, the sum from n equals 0 to infinity of minus 1 to the n, divided by n factorial gamma of 1 plus nu plus n, and then multiplied by x divided by 2 raised to the 2n plus nu. And as you can easily identify, this expression that we have here is just j sub nu of x, right? According to the definition that we gave here. Yeah. Well, this what we have here is just j sub nu of x. So we are going to get that x j sub nu prime of x is equal to nu j sub nu of x plus the sum from n equals 0 to infinity of minus 1 to the n. And here, look that we have an n divided by n factorial, but n factorial can be seen as n times n minus 1 factorial, right? So we can cancel an n with an n here. Okay, and this is going to take us to have a number 2 here, and then this is divided by n minus 1 factorial, gamma of 1 plus nu plus n, and then this multiplies x divided by 2 to the 2n plus nu. Perfect. And something that is very important in this step, right, is that notice that when we made the cancellation, we divided this whole thing by n, right? But we need to know, well, we need to be conscious that to cancel these n's, we cannot consider the element of the sum when n is equal to 0, right? Because we will be divided by 0 in this step. Okay? So if we will take the element of the sum n equals 0, we will only get 2 times 0, right? So that is 0. So that means that all this sum that we have here, all this sum actually can start at n equals 1, right? Because the 0 element is just 0. So that means that the sum that I wrote here doesn't start at 0. It starts at 1, right? Okay, perfect. Okay, so after saying this, we are going to reindex that sum to make it start at 0. You know that when you want to reindex a sum, you need to, for example, sum the quantity you want to add in this side, and then rest that quantity in the index count, okay? For example, let's say that I want this to be n plus 1. So that means that every n here needs to be changed for an n plus 1. But here we need to subtract a minus 1 in the index counting, right? So that means that if we want to start this sum as 0, we need to subtract 1 here. So this will be the sum from n equals 0 to infinity. And we need to add plus 1 in every n on the elements of the sum. So that will be minus 1 to the n plus 1, 2 divided by n plus 1 minus 1, right? Factorial. But this will be only n factorial, and then gamma of 1 plus nu plus n. That will be, we're going to leave it as 1 plus 1 plus nu plus 1. You will see why later on. And then x divided by 2, and then 2 times n plus 1 will be 2n plus 2 plus nu, right? Okay. And then we are going to make some tricks here. We are going to multiply by x divided by x. Yeah. Recall that this is generating 2 divided by x. So we can take this 2 divided by x to multiply here, right? Let me write it here, 2 divided by x. Okay, let me remove it. And let's say that we have just an x here. Okay. So this is in order to mix this element with this other element. Okay, so we will get nu j sub nu of x plus x, the sum from n equals 0 to infinity of minus 1 to the n plus 1 divided by n factorial gamma of n plus 1 plus nu plus 1. And then, well, we need to subtract a minus 1 right at the exponent. So it will be x divided by 2 and plus nu plus 1, right? And yeah, this is what we get. But notice that we have already constructed a very similar structure to what will be j sub nu plus 1 of x, okay? This is not exactly the same, but it is almost this expression. So we just need to take out a minus 1 from here, right? And that is easy to do. This will be nu j sub nu of x plus x, and let me take out this minus, right? Because we can see this as minus 1 to the n times minus 1. So we are going to take this minus out of the sum to get minus x, the sum from n equals 0 to infinity of minus 1 to the n divided by n factorial gamma of n plus 1 plus nu plus 1, and then x divided by 2n plus nu plus 1. Okay, perfect. So with this, we can identify all this expression as the Bessel function of order nu plus 1. Because according to the definition that we had, if we take the change of nu for nu plus 1, right, we will get well, exactly this expression that we found. So that means that x j sub nu prime of x is equal to nu j sub nu of x minus x j sub nu plus 1 of x. Okay, perfect. So yeah, I think this is already a very, very important result that you will see very often when you work with Bessel functions. Again, remember that we have been making some videos about the Bessel Fourier series, and we often use this relation that we have here. Okay, but we are not over yet. We are still going to work a little bit with this to find another two expressions that will also be useful. Okay, so what happens if we divide by x all this expression and take this to the left-hand side of the equation? We are going to get that j sub nu prime of x minus nu divided by x j sub nu of x is equal to minus x j sub, actually x divided by x, right? But that is minus 1. So j sub nu plus 1 of x. Okay, perfect. And you know that when we want to express some things in differential equations that involve the first derivative and the function here as the derivative of a product, we need to multiply by an integrand factor, right? In this case, that integrand factor will be the function x to the minus nu. So we are going to multiply all this equation by x to the minus nu. And we are going to get x to the minus nu j sub nu prime of x minus x to the minus nu minus 1 nu j sub nu of x equals minus x to the minus nu j sub nu plus 1 of x. Perfect. And we can easily identify that this is the derivative with respect to x of x to the minus nu j sub nu of x. Right? Just to verify, we are going to take the derivative using the product rule. This will be the derivative of the first function, which is minus nu, times x to the minus nu minus 1. And then this multiplies the second function, which is j sub nu of x, and then plus the derivative of the second function times the first function. Okay? So yeah, as we can see easily, this corresponds to what we have here. Perfect. So we can say that this derivative over here is equal to minus x to the minus nu j sub nu plus 1 of x. And this will be one other important result involving Bessel functions. Okay, perfect. So after showing this result, it's not very hard to show that the derivative with respect to x of x to the nu j sub nu of x is equal to x to the nu j sub nu minus 1 of x. Recall that this is another Bessel function, right? This is of order nu minus 1, while in this expression, we have the Bessel function of order nu plus 1, right? So again, it is not very hard to show. It can be done in a very similar way. So with this, we have found two important results of Bessel functions. Recall that these are recurrence relations that involves the derivative of the Bessel function. So again, it will be important to define the Fourier Bessel series. Okay, perfect. So I think that with this, I'm going to finish the lesson now.